So let's move on from here to the next topic, right? And it's not doing anything. There it goes. So there's an interrelation between light and heat, right? You guys know that if you stand under these fluorescent lights, it's not like you can feel a bunch of heat hitting you, right? But you guys probably also know that if you were to stand on a chair and you put your hand on the bulb on that projector, that before you even got to it, you would feel heat, and then you touch that bulb, it's hot. You guys also know that the sun is hot. But light has different types of energy in it, okay? So with sunlight, the heat is such a prevalent thing, right, that there's a very close interrelationship of it. When you look at these fluorescent lights, the notion of heat and light are kind of more separated, even though they will get hot, okay? So sources of light can include waves that are in what's called the infrared spectrum, okay? So they contain, I think I have a graphic for this, and I don't know if it's in here, but they contain different spectrum. They contain the ultraviolet spectrum at one end, the visible spectrum, that's the light that you see that actually illuminates things, and then there's the infrared that you don't see, okay? All right, so all forms of energy have some importance or relationship to how we build a building and why we build it the way that we do. And so we're going to be putting most of our focus on this idea of heat energy. And one of the areas of heat energy that we'll be looking a lot at is sunlight. Okay? So talking about energy, and again, we're getting this, I'm trying to move along as fast as I can here. So we talked about this the other day in that other video, that sources of energies can be divided into two different types, renewable sources and non-renewable sources. So renewable sources of energy are sources that are readily replenished. You can make more of it quickly, okay? The source is generally part of a natural process wherein you're capturing the energy as part of a natural process, okay? Non-renewable sources are fixed quantities. You can't make more. Once you've used all the uranium, it's gone. Once you use all the oil, it's gone. If you chop down every tree, there's no more wood, okay? The majority of the types of energies that we get from non-renewable sources, right, is generally petrocarbons or hydrocarbons, which are essentially prehistoric sources that are stored up sort of underneath the earth. Then there's the uranium we've talked about, and so there's no natural process that's making more uranium. There's no natural process that's making vast quantities of oil that we can turn into gasoline, okay? So looking at that, we've already kind of talked about this as I was talking about that. So petrochemicals, oil, gasoline, jet fuel, which is essentially a type of diesel fuel, hydrocarbon liquids like liquefied petroleum gas, natural gas, and nuclear energy. Those are all examples. Renewable sources of energy are solar energy, both in capturing as hot water and as creating electricity through photovoltaic. There is geothermal energy, and that is energy that is part of the earth. And technically, the earth will eventually, the core of the earth will eventually cool. And so you could think of that as not renewable, but I mean, I don't know what will be on the planet, on the face of the planet when that happens. It won't be humans. Okay, that's billions and billions of years from now. All right, wind energy. So, obviously many of you have gone out to Palm Springs. You've seen those big whirly things, and they create electricity. Biomass and bioenergy. Anybody drive like a fairly late model GM vehicle? No, that's not late model, buddy. So, does anybody ever seen a thing that says flex fuel?
Oh, yeah.
Right? Well, what flex fuel is essentially a type of biofuel, or a mixture of biofuel. Actually, every single car that uses gasoline in California is using some biofuel, because they're adding ethanol to the gasoline, and ethanol is made from corn. That's right. It's made from corn. It's from Iowa. Is it Iowa? I don't know. I think so. And hydropower, which when you guys know that a dam can make electricity, you know that back in the day they created these little water wheels and they spun around and then the pirates got on them. No, Pirates of the Caribbean. No, the scene where they're Never mind. Continuing on. Okay, one thing we talked about the other day we didn't go into depth on it is this notion of embodied energy. Okay, so that is where one type of energy is used extensively to make a product, and that product really now it has a function of that energy stored up in it. Okay, so coal mining and transporting it is an example of this thing. You got to dig the coal out of the ground, you got to transport it, then you got to burn it. The coal has a lot of embodied energy in it. How many of you guys have ever walked under high voltage lines and you hear them going bzzz? Something's vibrating to make that noise, right? So that is a form that's a form where you can see electricity, right? Or you can hear electricity being lost from something where it's sort of embedded inside of it. Okay, it's being turned into another form of energy. All right, that didn't make a lot of sense. That's a bad analogy. I'm gonna have to change that. All right, secondary energy sources, right? Very specific type of embodied energy includes forms of energy that are made from other sources of energy. So, for example, we talked about the fact that the majority of coal-fired power plants are making what? Electricity, right? They're making electricity. So we're using one form of energy, which is coal, and we're transferring it or transforming it into another form of energy. So that in and of itself is kind of a problem, right? Remember the other day I asked you about the laws of thermodynamics? So in this particular case, we had to mine the coal, then we had to process it so that we could burn it, then we had to get it to the plant. Somebody had to use up all of their breakfast to load that thing into the, into the burner, and then we finally burned it, and then we made electricity out of it. So we used this huge amount of energy, right, just to turn it into a form of energy that we could use. All right? So let's take a look at the laws of thermodynamics, or some of the laws, because there's either 3 or 4 depending on how you look at the base law, but let's stick to the simple one, right? The first one is the law of conservation of energy, and it states that energy can either be created or destroyed. Energy can be transferred from one form to another, but you cannot make more energy. The amount of energy that exists in the universe is constant. There's no more, no less. Where it goes is a different story, okay? The law of entropy. When you paraphrase that for our studies is that there is never a 100% efficiency when you transfer energy from one form into another. There's always some level of loss. A different way of interpreting the law of entropy is that everything is going to find its lowest form or its lowest level of potential energy. That's a little bit more kind of complicated. So I've got something written up there that says a coal-fired electrical generation plant is only about 35% efficient. So if we could measure energy as a quantity, right, of coal, we would find that in order to burn it to make electricity, we lost 65% of it. The majority of that loss is to heat that can't be captured. Okay? All right. Pretty much done with this thing. We're going to look more closely at the laws of thermodynamics in our next lecture, which is heat, which I don't know that I'm going to get to, but we'll try. So let's stop that sucker. Stop.